Welcome to chemistry, indicators and their color changes. Imagine being able to tell whether a solution is acidic or basic just by looking at its color. That is exactly what indicators allow us to do. Acid-base indicators are chemical compounds that change color depending on the pH of their environment. They are weak acids or weak bases whose undissociated form has a distinctly different color from their dissociated form. In this presentation, we will explore the chemistry behind indicators, how they work through acid-base equilibrium, the pH ranges of common indicators like litmus, phenolphthalein, methyl orange, and bromothymol blue, how to select the right indicator for titrations, and even natural indicators like red cabbage and turmeric. Through 5 quiz questions and 5 fully worked problems, you will master this colorful topic. What exactly are acid-base indicators? An acid-base indicator is a halochromic chemical compound that is added in small amounts to a solution so that the pH can be determined visually by a color change. Most indicators are weak organic acids or bases. The general formula for an acidic indicator is Hind, where Hind represents the acid form and End- represents the conjugate base form. The acid form has one color and the base form has a different color. When the pH changes, the equilibrium shifts according to Le Chatelier's principle. Adding acid increases the concentration of hydronium ions, shifting the equilibrium to the left toward the Hind form, producing color A. Adding base removes hydronium ions, shifting the equilibrium to the right toward the Nd- form, producing color B. The human eye typically detects the color of one species when it is about 10 times more concentrated than the other, which gives a transition range of approximately pKa plus or minus 1 pH unit. The pH scale ranges from 0 to 14 at 25 degrees Celsius, with 7 being neutral. Each pH unit represents a 10-fold change in hydronium ion concentration. The lower the pH, the more acidic the solution. The higher the pH, the more basic it is. Each indicator has a specific pH range over which it changes color. For example, phenolphthalein changes from colorless to pink between pH 8.3 and 10.0, making it perfect for detecting bases. Methyl orange changes from red to yellow between pH 3.1 and 4.4, making it ideal for detecting acids. The transition range of an indicator is determined by its acid dissociation constant Chi. The midpoint of the transition occurs when pH equals pKk. Different indicators cover different portions of the pH scale, and by using a combination of indicators, we can estimate pH over a wide range, as with universal indicator. Here is a comprehensive look at the most common acid-base indicators used in chemistry laboratories around the world. Litmus is a natural mixture of dyes extracted from lichens, changing from red in acid to blue in base with a transition between pH 4.5 and 8.3. Phenolphthalein is synthesized from phthalic anhydride and phenol. It is colorless below pH 8.3 and pink above pH 10.0. In very strong bases above pH 12, it becomes colorless again. Methyl orange is an azo dye that is red in strongly acidic solutions below pH 3.1 and yellow above pH 4.4. Bromothymol blue is a sulfonthaline dye that is yellow in acid, green at neutral pH 7, and blue in base. It is excellent for detecting carbon dioxide in solution. Thymol blue has 2 color changes, red to yellow at pH 1.2 to 2.8, and yellow to blue at pH 8.0 to 9.6. The choice of indicator depends on the expected pH range of the solution being tested. The color change of an indicator is fundamentally a molecular transformation. In acidic conditions, the indicator molecule exists in a protonated form with a specific molecular structure that absorbs certain wavelengths of visible light. When a base removes the proton, the molecular structure changes, typically through the rearrangement of double bonds and the extension or disruption of conjugated pi electron systems. For phenolphthalein specifically, the colorless lactone form has an sp3 hybridized central carbon that breaks conjugation between the aromatic rings. When deprotonated in basic solution, the lactone ring opens, creating an extended conjugated system spanning all 3 aromatic rings. This conjugated system absorbs light in the visible range, giving the characteristic pink color. In very strongly basic solutions above pH 12, further deprotonation creates a carbonyl form that once again breaks conjugation, returning the solution to colorless. Choosing the right indicator for an acid-base titration is crucial for obtaining accurate results. The key principle is that the indicator's transition range should overlap with the pH at the equivalence point of the titration. For a strong acid titrated with a strong base, the equivalence point pH is exactly 7.0, and the pH curve shows a very sharp vertical change. Any indicator with a transition range near pH 7 will work, such as bromothymol blue or Litmus. For a strong acid titrated with a weak base, the equivalence point is below pH 7 because the conjugate acid of the weak base makes the solution slightly acidic. Methyl orange, with its transition in the range pH 3.1 to 4.4, is the ideal choice here. For a weak acid titrated with a strong base, the equivalence point is above pH 7 because the conjugate base of the weak acid hydrolyzes to produce hydroxide ions. Phenolphthalein, with its transition in the range pH 8.3 to 10.0, is the standard choice. Titrations of weak acids with weak bases have poorly defined equivalence points and are rarely performed in practice. Nature provides a beautiful array of natural pH indicators. The most famous is red cabbage, which contains anthocyanin pigments that change color across a wide pH range. In strongly acidic conditions below pH 3, red cabbage juice turns a vibrant red. As pH increases towards 7, it shifts through pink and magenta to purple at neutral pH. In basic conditions, it turns blue around pH 8 to 9 and green to yellow above pH 10. Turmeric contains curcumin, which is yellow in acidic and neutral solutions, but turns reddish-brown above pH 7.4. Turmeric paper is a simple DIY indicator. Litmus itself is a natural indicator, extracted from lichens of the species Roxella. The color of hydrangea flowers is also pH dependent. In acidic soil, they produce blue flowers, while in alkaline soil, they produce pink flowers. This is because aluminum ions become more available in acidic soil and are absorbed by the plant, forming blue complexes with anthocyanins. Universal indicator is a mixture of several individual indicators carefully blended to produce a continuous range of colors across the entire pH scale from 0 to 14. The classic formulation contains thymol blue, methyl red, bromothymol blue, and phenolphthalein in a water alcohol solution. At pH 1 to 3, the mixture appears red, indicating strong acidity. Between pH 4 and 6, it transitions through orange to yellow, indicating weak acidity. At pH 7, it is a neutral green color. In the pH range 8 to 10, it shifts through blue to indigo as basicity increases. Above pH 11, it becomes violet, indicating strong basicity. pH paper, often called litmus paper, comes in red and blue forms. Red litmus paper turns blue in basic conditions. Blue litmus paper turns red in acidic conditions. For more precise measurements, wide-range pH paper impregnated with universal indicator provides a color comparison chart printed on the packaging. Quiz question 1. Which indicator is colorless in acidic solution and turns pink in basic solution? Option A, methyl orange. Option B, phenolphthalein. Option C, bromothymol blue. Option D, litmus. Quiz question 2. The pH transition range of an indicator is approximately Option A, pKa plus or minus 0.5. Option B, pKa plus or minus 1.0. Option C, pKa plus or minus 2.0. Option D, pKa plus or minus 3.0. Quiz question 3. Which indicator is most suitable for titrating ammonia with hydrochloric acid? Option A, phenolphthalein. Option B, bromothymol blue. Option C, methyl orange. Option D, thymolphthalein. Quiz question 4. Bromothymol blue is added to an unknown solution and turns green. What is the approximate pH? Option A, pH less than 3. Option B, pH approximately 7. Option C, pH greater than 10. Option D, pH approximately 5. Quiz question 5. A student adds red cabbage juice to 3 solutions. Solution A turns red. Solution B turns purple. Solution C turns green. Which statement is correct? Option A equals pH 2, B equals pH 7, C equals pH 12. Option B, A equals pH 12, B equals pH 7, C equals pH 2. Option C, A equals pH 7, B equals pH 2, C equals pH 12. Option D, A equals pH 12, B equals pH 2, C equals pH 7. Problem 1. pH from indicator color. An indicator Hind has Ka equals 2.0 times 10 to the negative 6. In a solution, the ratio of Ind minus to Hind is 0.25. Calculate the pH of the solution. Step 1. pKa equals negative log of Ka. Step 2. pKa equals negative log 2.0 times 10 to the negative 6 equals 5.70. Step 3. Using the Henderson-Hasselbalch equation, pH equals pKa plus log of the ratio. Step 4. The log of 0.25 is negative 0.602. Step 5. Therefore, pH equals 5.70 minus 0.602 equals 5.10. The answer is pH equals 5.10. This is within the pKa plus or minus 1 range, so both colors would be visible. Problem 2. Indicator selection for titration. 50.0 milliliters of 0.1 molar acetic acid with Ka equals 1.8 times 10 to the negative 5 is titrated with 0.100 molar NaOH. Calculate pH at equivalence and choose a suitable indicator. Step 1. At equivalence, all acid has been converted to acetate ion. The total volume is 100.0 milliliters. Step 2. The concentration of acetate is 0.0500 molar. Step 3. Kb for acetate equals Kw divided by Ka, which equals 5.56 times 10 to the negative 10. Step 4. The hydroxide concentration is the square root of Kb times acetate concentration. Step 5. This gives 5.27 times 10 to the negative 6 molar. Step 6. pOH equals 5.28, so pH equals 14.00 minus 5.28 equals 8.72. The answer is pH 8.72. Phenolphthalein, with its range of 8.3 to 10.0, is the suitable indicator. Problem 3. Ka from indicator data. An indicator is red in its acid form and yellow in its base form. At pH 5.0, the solution appears orange because both colors are equally intense. Calculate the Ka of the indicator. Step 1. Equal color intensity means both forms are at equal concentration. Step 2. When concentrations are equal, the ratio of Ind minus to Hind equals 1. Step 3. From the Henderson-Hasselbalch equation, pH equals pKa plus log of 1, so pH equals pKk. Step 4. Therefore, pKa equals pH, which equals 5.00. Step 5. K equals 10 to the negative pKa equals 10 to the negative 5.00, which is 1.00 times 10 to the negative 5. The answer is Ka equals 1.00 times 10 to the negative 5. Problem 4. Multiple indicators. A solution turns methyl orange yellow, phenolphthalein colorless, and bromothymol blue-blue. Estimate the pH range. Step 1. Methyl orange is yellow above pH 4.4, so pH must be greater than 4.4. Step 2. Phenolphthalein is colorless below pH 8.3, so pH must be less than 8.3. Step 3. Bromothymol blue is blue above pH 7.6, so pH must be greater than 7.6. Step 4. Combining all three constraints, pH is greater than 7.6 and less than 8.3. Step 5. The answer is pH between 7.6 and 8.3. The solution is slightly basic. Problem 5. Titration with indicator. 0.450 grams of an unknown monoprotic acid is dissolved in water and titrated with 0.150 molar NaOH. The phenolphthalein endpoint is reached at 24.8 milliliters. Calculate the molar mass. Step 1. The phenolphthalein endpoint confirms a basic equivalence point. Step 2. Moles of NaOH equals 0.150 molar times 0.0248 liters, giving 0.00372 moles. Step 3. Since the acid is monoprotic, moles of acid equals moles of base, which is 0.00372 moles. Step 4. Molar mass equals mass divided by moles equals 0.450 divided by 0.00372. Step 5. This gives 121 grams per mole. The answer is a molar mass of 121 grams per mole. Let us consolidate everything we have learned about acid-base indicators. Indicators are weak acids or bases whose protonated and deprotonated forms have distinctly different colors. The equilibrium Hind plus water reversibly forms H3O++ Ind-, shifting according to Le Chatelier's principle. The Henderson-Hasselbalch equation, pH equals pKa plus log of the ratio of base form to acid form, describes the relationship between pH and indicator color. The transition range of an indicator is approximately pKa plus or minus 1 pH unit. Common indicators include litmus from pH 4.5 to 8.3, phenolphthalein from 8.3 to 10.0, methyl orange from 3.1 to 4.4, and bromothymol blue from 6.0 to 7.6. For selecting indicators and titrations, choose one whose transition range overlaps with the equivalence point pH. Strong acid plus strong base, use bromothymol blue. Strong acid plus weak base, use methyl orange. Weak acid plus strong base, use phenolphthalein. Natural indicators like red cabbage and turmeric provide colorful alternatives. Mastering indicators gives you a powerful visual tool for understanding acid-base chemistry.